Welcome back to Future Minds Gen AI Data Science Podcast. I'm your host Mano. I'm excited to have you with me for our 10th episode. In our last discussion, we delved into natural language processing, exploring how machine understand, interpret, and generate human language. Today, we are going to take another leap forward by examining one of the most fascinating and impactful application of AI, reinforcement learning. This area of AI has been instrumental in achieving significant breakthrough in various fields, including gaming, robotics, autonomous system. So let's dive in. Reinforcement learning RL is a type of machine learning where agent learns to make decisions by performing actions in environment to achieve maximum cumulative reward. Unlike supervised learning where the model learns from labeled data, RL learns from consequences of action, which makes it particularly suitable for tasks requiring sequential decision making. To begin with, let's outline the basic component of reinforcement learning. The first one is agent, the learner or decision maker that interacts with environment to perform action. Second is environment, the external system that the agent interacts with and which provide feedback in the form of reward and penalties. Third is state, a representation of current situation or configuration of the environment. Fourth is action, the set of all possible moves the agent can make. Five is reward, feedback from the environment in response to the action, indicating the success or failure of the action. 6 is a policy, a strategy that defines the agent's action to each state. 7th is value function, a measure of the expected cumulative reward from given state, guiding the agent to make better decision. Now let's discuss the concept and methodology in reinforcement learning, the Markov decision process, MDP. Reinforcement learning problems are often modeled using the Markov decision process, MDP. An MDP provides mathematical framework to describe environment in RL. It consists of set of state and set of actions and reward function and set transition probability. State transition probability, this define the probability of transitioning from one state to another given specific action. It encapsulates the dynamic of the environment. Type of reinforcement learning, model free RL and model based RL. Model free RL, the agent learns policy directly from interaction with environment without any knowledge of environment dynamics. Example include Q learning and SARSA. The model based RL, the agent learns from model environment's dynamic, use it as a it plan action. It typically requires fewer interaction with environment but can be more complex to implement. On policy versus off policy RL. On policy RL, the agent learns the value of policy being followed, including any exploratory moves. An example is SARSA, state action reward, state action reward. Of policy RL, the agent learns from the value of optimal policy independent of the agent action. A common example is Q learning, exploration versus exploitation. A central challenge in RL is a trade off between exploration, trying to new action to discover their effects, and exploration using a known action that yield the high reward. Effective RL strategies balance these two aspects to optimize performance over time. The Q learning. Q learning is a model free and off policy RL algorithm that seeks to learn the value of action particular state. The Q value or action value function represent the expected utility of taking given action in the given state following the optimal policy thereafter. Q value is updated using Bellman equation where alpha is the learning rate, gamma is the discovered discount factor, R is the reward received after taking action A, and state S, and S dash is the new state after taking action. Deep reinforcement learning Deep reinforcement learning combines RL with deep learning. The most notable example is Deep Q network (DQN), which use the neural network to approximate Q value function. This approach has been highly successful in the playing the games like Atari and Go. The DQN Q value approximated using neural networks, and the weights of the new network are updated using gradient descent. Policy gradient method. Policy gradient method directly parameterize the policy and optimize the policy parameters through gradient expect in unexpected reward. This is different from q-learning, which optimize the value function. Policy gradient methods are particularly useful for high dimensional action spaces and continuous action problem. Application of reinforcement learning. Gaming RL has been extensively used in gaming. Notable successes including AlphaGo by DeepMind, which defeated world champion in the game of Go. RL is also used in the video game AI to create adaptive intelligent opponent. Robotics RL enables robots to learn complex tasks such as walking, grasping, and navigating through trial and error. By interacting with their environment, robots can adapt to new tasks and improve their performance over time. Autonomous vehicles RL is used to train autonomous vehicle to make decisions in dynamic environment. This include tasks like lane changing, obsolete avoidance, and optimal path learning planning. Finance RL algorithm are applied in trading strategy, portfolio management, and automated financial decision making. They learn to optimize investment return by exploring different trading action, adapting to make changes. Healthcare RL can assist its personalized treatment plans, optimizing drug dosage, and improving patient outcome through adaptive and data driven decision making processes. Challenge and future directions. Sample efficiency. RL often requires large number of interaction with environment to learn effectively, which can be impractical in a real world application. Safety and ethics. Ensuring the RL agents make safe and ethical decisions, especially in critical areas like healthcare and autonomous driving, is crucial. Scalability. Scaling RL algorithm to complex and real world environment remain a significant challenge. Generalization. RL agent often struggle to generalize learn behavior to new unseen environment. Improving generalizing capabilities is ongoing area of research. Promising research direction. Meta reinforcement learning. Meta RL focuses on enabling agents to learn new tasks quickly by leveraging prior experience. This involves training agent on distribution of tasks so they can adapt rapidly to new ones. Multi-agent reinforcement learning. This involves multiple agents interacting within same environment and learning to cooperate and compete. It has applications in areas like autonomous driving where multiple vehicles need to coordinate. Hierarchical reinforcement learning. This approach decomposes complex tasks into simpler subtasks, making it easier to agent to learn, manage their action. Combining RL with other AI techniques, integrating RL with other AI methodologies such as supervised learning, unsupervised learning, uh, NLP can create more robust. So, thank you for joining me today for Future Minds GenAI Data Science podcast. I hope you found this exploration of reinforcement learning as captivating and enlightening as I did. Make sure subscribe my channel so you don't miss any future updates. Until next time, I'm Mano signing off. Stay curious, stay inspired. Thank you.